Good day, worldwide university students. Welcome to the channel of Massive Quality Mathematics, where we abuse mathematics by finding solutions. Today, I want to take you through the course called Linear Algebra, specifically through the topic called vector spaces, as projected on the screen. So under the course Linear Algebra, I will make several videos covering the following topics or subtopics: vector spaces and subspaces, inner product spaces, linear transformation and diagonalization, eigenvalues, eigenvectors and orthogonality, matrices, determinants and inverses, and many more. So feel free to inquire anything about the course. You can write your questions in the comment sections, and I promise your questions will be highly considered and responded in due time. So we can go through the course. Now we'll start with an introduction to vectors. So in the early grades or high school, those who studied, obvious, if you are doing mathematics, you studied maths and science in lower grades. So we talk about physical science, they talk about vectors and scalars. So the traditional difference between a vectors and scalar is direction. So we used to define a vector as a physical quantity that has both magnitude and direction, but a scalar is a physical quantity that has magnitude only. So these are the basic principles that are distributed in high school. So now I want to take you through introduction to vectors. You know the notation of vectors. So the notation of vectors can be what called any letters with an arrow on top showing the direction, any letters with an arrow on top, or you can just bold. You can have a bold letters if you don't want to put an arrow on top. So but a scalar is any letter written in anyhow without a direction, just like C, D, whatsoever. So they can be any letters. So now, introduction to vectors. Let me enlarge the screen. So now, introduction to vectors. Bear in mind that the heart of linear algebra is in both two basic vector operations, namely vector addition and scalar multiplication. So is an addition plus and star, which is a scalar multiplication. So these are the cornerstones of linear algebra. The cornerstones of linear algebra are the two basic vector operation, namely vector addition and scalar multiplication, meaning that we can be able to add two vectors and we can also be able to multiply a vector by a scalar. So now let's talk about vector addition individual. Let's take the individual operations. So now vector addition. Suppose we have two vectors u and v inside two dimension. So because this is the two dimension, R2, it is just the dimension. It means that these two vectors has two components. The components of vectors are two because they are in two dimension. They are in R2. In other words, they are in XY plane. Like these x-axis, y-axis, two components. So they are in R2. So they are in XY plane. Suppose we have these two vectors u and v in R2, then we can add two vectors like this. U plus v is equals to, you know what we have. This is a vector with two components, which is u1, u2. They are components. So the components are written inside. So there are two notations of a vector. A vector can be represented as a column vector, or it's like this. We can say u is equals to u1, u2, where these are components. I can say u is equals to v1 u1 u2. So you can represent a vector as a column vector 2. So now u plus v can be added together like u1 u2 plus v1 v2. Those are the components. You add the component wise. That's what you do. You add what you call component wise. So you add what you call add corresponding components. You add what you call corresponding components. So u1 with v1 and u2 with v2. That's how we add two vectors, and that's what is definitely happening here. So now that's simple. We can take any two vectors. For example, if we say u, example, if we say u is 2 and 3, v, or let me write it in a new script. If we say u is 2 and 3, and we say v, it's -1 and 5. So we can add two vectors like this, u and v like this. U plus v is 2 and 3. They are vectors in R2, plus -1 and 5, which is equals to 2 plus -1, then 3 plus 5. This is just equals to 2 minus 1, which is 1, and 8. So this is a vector u plus vector v. That's what we're simply talking about. So now, going on, we have what we call scalar multiplication. So the scalar multiplication is all about multiplying a vector with a scalar. Suppose we have two scalars, C1 and C2, belonging to a real number, because scalars are real numbers. That's what called scalars are real numbers. Bear in mind that note NB, scalars are always real numbers. Scalars are always real numbers. So suppose we have given these two scalars belonging to real number and vectors u and v in 2 dimensions as previously. Then we multiply c1 and c1 and u and c2 and v to get what the following. So it is c1 multiplied by u, which is c1, and we put that vector with two components u1 u2. It equals to, we multiply what we call the corresponding what? Corresponding components. We multiply corresponding, or let's say each corresponding component by a scalar. So that's what to do. That's what is happening. That's why we've got c1 multiplied by u1, which is c1 u1, then c1 multiplied by u2, which is c1 u2. And also this same applies to v. You can do the same thing. C2 times v, a vector v, it equals to c2 into v1 v2, which is just equals to c2 v1, then and the c2 v2. So we multiply a scalar by a vector in a certain dimension. That dimension will still be the same. The dimension won't change. If we're multiplying a scalar by a vector in a certain dimension, the dimension remains the same, but we just multiply each corresponding component by that scalar. So that's what is happening. Now let's talk about a well-celebrated subtopic in linear algebra called linear combination. So let's talk about linear combination. So the linear combination is the sum of, or is the combination of vector addition and scalar multiplication. So the sum of C1 U and C2 V, that is these guys. So if we add them together, this is what called the linear combination of two vectors, which is what? Vector U and vector V. So we have these scalar multiplication. So the moment we add them together, now they form what called a linear combination of U and V. For example, if we have got U plus V, then we're multiplying them by a scalar which is C, like a column vector. This is the same as, you can write it as the same as like this is the same thing, there's no problem. And also this one you can write it as 2 3 is the same thing, there's no problem. So U plus V equals to C1 into a vector with two components 1 1 plus D, a column vector with two components 2 and 3. This is equals to, just we multiply here, this multiplied by this component wise. So we multiply each corresponding component by a scalar C. So this is C because we multiply 1 by C and 1 by C, plus multiply each component by D, 2D, 3D, and we add them. So that's what we call the linear combination, adding the two scalar multiplication together. This is a combination with scalars C and D. So that's what we're talking about. So you can also write this thing represent this thing in this way. We have what called U is, for example, plus V. This is just equals to C. You can say it's just a 1 1 plus D. You can just is 2 3. This is just what called C when you multiply each component, plus 2D 3D when you multiply. So this is just equals to, we know how to add the vector addition, two vectors, then we add the corresponding components together. This is C plus 2D together, this one plus this one, then C plus 3D together, and this is a combination with scalars C and D. So that's how what we are talking about. So now another example we can give it here, which is U plus V. This is just 1 1. You can also denote it like this, plus 2 3, denote it like this. This will be equals to 1 plus 2, which is 3, and 1 plus this one, which is just 4, which is just what we call these plus these, which is just 1 plus 2 3, 1 plus 3 4. Then this is a combination again with C equals to D with two scalars. This scalar C equals to scalar D equals to 1. They are just 1. So that's what we are talking about. So let's talk about a vectors and linear combination. As I said before, there's an important point that we want to highlight here. So is that a linear combination, it's all about combining addition, vector addition, and scalar multiplication. It's all about combining what? Vector addition and scalar multiplication. So when you combine these two, we now form what we call linear combination. So this is defined also mathematically above. We define it there. So now for special linear combination, let's talk about the special linear combinations. Let's talk about special linear combinations. Special linear combination. This is a simple linear combination. We've got what called the sum of vectors, which is just 1 times U plus 1 times V. These are sum of vectors. We've got the difference of vectors. This is just with scalar, or with the same scalar, which is 1. 1 belongs to real number. Remember, we told you that the scalar is always a real number. So now we've got a 0 vector. You know what is a 0 vector? If we talk about the 0 times U plus 0 times V, it becomes 0. So now we also have got what called C times U plus 0 times, this is a vector CU in the direction of U. That's a simple thing. You know that this is going to tend to 0. So a 0 vector plus a vector, because this one is also a vector, it's also that vector. So that's the special linear combinations that we can talk about. So now you know what called the dimensions of a vectors. So now let's just go through the review of the key ideas. So what is really happening here? So the review of the key ideas of what we have covered so far. So now a vector V in two-dimensional space has two components, V1 and V2, as I demonstrated above. So now that's like, if you just like if you have u plus v, yeah, it should be u plus v, sorry. If we have u plus v, this is v, this is the same as, you know that u plus v is the same as u1 u2 plus v1 v2, which is just what we call u1. You know that u is a vector in 2 dimensions, which is u1 u1 u. Let me write it here. You know that u is u1 has 2 components, u1 u2, and v has 2 components, v1 v2. That's why we have what called, when we're adding u and v, now we have what called u1 plus v1 and u2 plus v2. So also we can have what called scalar multiplication. This one is very important. That is c times v, which is the same as, just like if you want to write these steps, you can just say it's this. It's first is c into v1 v2 before you write that step. So that means it's c times a vector with 2 components, v1 v2, then we multiply the corresponding components with by a scalar. That is c times v1, which is this, and c times v2, which is that, c times v2. So a linear combination of 3 vectors u, v, w is written as c1 times vector u plus c2 times vector v plus c3 times vector w, where c1, c2, and c3 are scalars. So c1, c2, c3 belongs to R, to real number. They are scalars. So take all linear combinations of u or v or v like that in 3 dimensions. Those combinations typically fill a line, then a plane, then a whole space. So that's what they're talking about this point. So now we want to talk about the important thing here now, that is called what called vector spaces. So now vector spaces, what is a vector space? So that's the important question. I have two definitions. So a vector space is the set of vectors with rules for vector addition and scalar multiplication. So it's the set of vectors with rules for vector addition and scalar multiplication. So that's a set of vectors with rules for vector addition and scalar multiplication. So mathematically we can say the non-empty set may be V, because V is equals to these set of vectors with vector addition and scalar multiplication, and also they specify what called a dimension. So the non-empty set, these on which 2 operations, vector additions and scalar multiplications, are defined, is called what called a vector space. So the non-empty set, these on which 2 operations of additions and scalar multiplications are defined, is called vector space. That's what is a vector space. That's what a vector space is. So it's a set of vectors with rules for vector addition and scalar multiplication. Those vectors inside the set, they can be added together and they can be multiplied with a scalar. So that's what we're talking about. So this Rn is just for dimension, that is in nth dimension, in n dimension. Then plus is for vector addition, and these multiplication is for obvious scalar multiplication. So now let's go to examples of a vector of vectors. So we've got example of vectors. So we've got what called R, which is the set of all real numbers. You know that is the set of all real numbers. So R2 is the set of all of ordered pairs. We can have vector space in R vector space where vectors are in R2, like what called V1, V2. If we've got what called a vector V, that's what we're talking about. So now R3 is the set of all ordered triples, or so we can have also V with 3 components, V1, V2, v3. That's what we're talking about. They are inside what? R3. So Rn is the set of all n tuples. So we can have v equals with the nth components v2, v3 up to what we call vn. They're also inside Rn. We can have the set of all polynomials. So we can have vector inside polynomial. So we can say p, maybe p is as a vector. Let me do this. We can have p as a vector inside what called p maybe 3. So meaning that is a p3. So down here. So p3 like this. This is a vector, like this is a polynomial px equals to what? You know, it can be what to call it can be what to call, where do I start? Let's start with a x cube plus bx squared plus c x plus d. So that's just a polynomial with degree 3 or degree 3 and less. So that's what we're really talking about. So now we can also have got the set of all polynomials with degree less or equals to n. That's what we're talking about. We've also what called the set of all n by n matrices. So we can say we have M23. This is a non-square matrix, we know. So if we have what called M23, for example, we can have A. If you say A and B, they are matrices. They are matrices, but in the form of vectors belonging to M2, 3. So we mean that this is 2 columns and 3 rows. So that means A can be any matrix with 2 rows and 3 columns. That is A or B, C, D, E, F. So you know that a matrix is represented by a capital letter and the entries can be represented by small letter. So that's, for example, that we're talking about. And also B, we can talk about any other thing like X, Y, Z, or X, Y, Z, W, T, or P. So this is still the matrix in M22. So also we can talk about what to call the what to call the square. We can talk about the square. Why is it not clearing this thing? So it's not a big deal. So let me fix this. Okay, you can just go back. So now we've got the set of all square matrices. You know the square matrices, if we have got what called A and B belonging to M22, you know that what we mean is that A can be M22, 2 rows and 2 columns. That is A, B, just C, D. So that's A. So that's a set of all square matrices. Those are examples of a vector space. As you can see, all of them, and we're going to deal with each and every one when we're doing examples, proving that a vector, a vector space is a subspace of another vector space, or is contained inside another vector space. So now let's talk about the properties of vector operations in Rn. So we need to talk about the properties of vector operations. So a vector V is denoted by V equals to V1, V2 up to Vn, and a 0 vector has got 0 components. That's a 0 vector. It has a 0 components. You can see 0, 0 up to 0 because we're talking about in Rn, that is an nth dimension. This is n dimension. This is n dimension. So now the definition, this thing is misbehaving, sorry. So I'm sorry. Yeah, so we are here. So now what we are saying is that we have got what called the properties of a vector, operations in R. So we have V in n dimension, which is just V with nth components, V1, V2 up to Vn, as you can see. And we've got a zero vector with n components, but there are zero component. That's a special vector with zero components, so 0, 0 up to 0. So the definition, we've got what called the equality of vectors. So the equality of vectors, or equal vectors. So two vectors can be equal, but when do we say two vectors are equal? So that's what called the important question. So that we can ask, that when do we say two vectors are equal? Two vectors U, which is U1, U2 up to Un, and V, which is V1, V2 up to Vn, belonging to what called Rn, which is the dimension of a vector, the nth dimension, are said to be equal. That is, U equals to V if the corresponding components are equal. So these vectors will be equal if the corresponding components are equal. That is, this vector is equal to this if U1 is equals to V1, U2 is equals to V2, etc. and etc. So that's why we have U1 equals to V1, U2 equals to V2, up to Un equals to Vn. For example, so we can have what called vector U as 2 and 3 and V as 2 and 3. These vectors are equal. We can conclude that U is equals to V because 2 is equals to what? Since 2 is equals to 2 and 3 is equals to 3. So these two vectors are equal. So but if we have 4 here like this, these two vectors are now not equal because the corresponding components are not equal, because 4 is not what? 4 is not equals to 3. So these two vectors are not equal. So U cannot be equals to V. So that's what we're generally talking about. Now let's move on. That is the equality of vectors. So the definition, that's a property. We can give it in the form of definition. Let U be equals to U1, U2 up to Un. Those are vectors in Rn. You can see be any two vectors. And let K be inside the real number, be a scalar. You know that a scalar is a real number. Then we define the following. We have U and V. Then we define the following. So we have what we call U plus V. That's adding these two vectors, like adding them, like U1 plus V1, U2 plus V2, the up to Un plus Vn. So that's what we are talking about. That's adding two vectors. We have talked about adding two vectors. The difference is that here is in what? Rn and n dimension. So that must not confuse you at all. So it is just that we are adding the corresponding vectors, following the same principle, following the same procedure. So then that's quite simple. So now also we've got subtraction. We can subtract two vectors like this. Subtract the component wise, like so, corresponding components. We subtract corresponding components. You can also scalar multiplication. You're familiar with these. So we've got what called the negation of a vector. So that is multiplying by -1. We can also just multiply as normal by -1. So now we need to talk about the theorem. This is a very important theorem, which is the properties of vector addition, abbreviated as VA, and scalar multiplication, or they are called what called 10 vector space axioms. They are called what called 10 vector space axioms. So this is very important theorem. So please follow, just listen to me here very attentively and follow whatsoever that I'm doing. So now this is the thing. If we let three vectors u, v, w belongs to Rn, remember in this case Rn is n dimension. Talk about this one. N dimension just means a vector has n components. Vector has n components. So that's what we mean. A vector has n components. And these C and D, let them be a scalar. They're inside the real numbers. They are scalars. Then the following properties hold. The following properties hold. The following properties hold. These are the following. We can number them 1, 2 because there are 10 vector space axioms. So if you don't want, you can name them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They are what called 10 vector space axioms or properties of vector addition and what we call scalar multiplication. So now, if we have got three vectors inside Rn and scalars C and D inside the real number, then the following properties hold. So one, the first property is called closure under vector addition. So u plus v, they belongs to, if we take two vectors, or we say this vector belongs to a vector space V, and also this V belongs to a vector space V. A set is represented by capital letter. Remember, a vector space V is a set which contains two rules. It's the set of vectors with two rules for vector addition and scalar multiplication. So a V, this big V is a vector space. It's a vector space. Now it's a set of vectors. But in this set of vectors, there are operations, two operations, which is a vector addition and scalar multiplication. That's why we're adding. We're saying that u plus v, if this individual vectors u belongs to v and v belongs to v, it means its combination also belongs to what go to a vector space v. Remember, Rn is an example of a vector space. So they're in Rn, it means they're simple also in v. So that's what we're talking about. So now, if we have u plus v if you have u belongs to v and v belongs to v, the u is a vector, v is a vector, that belongs to a vector space. So the combination or the sum of these two also belongs to v. This is called the closure property under vector addition. This same applies to real number. For example, if I can go outside of this content and go to the world of real numbers, or to the field of real numbers. So if we've got 2 belongings to R and 5 belongings to R, they are real numbers. 2 plus 5, it's 8. It also belongs to R. That means the R is closed under addition. So that's what we call a closure property under vector addition. So if you take two vectors inside what called inside a vector space, maybe Rn, and add them, we also get what called a vector space, which is a closure. We'll also get the sum of vectors inside a vector space, which is called a closure property under vector addition. So the second property that we can talk about is commutative property. So this is a very simple property. Let's say commutative property. You know commutative property. So now u plus v is the same as v plus u. This is a commutative property. It doesn't matter. So if one add u plus v and the other one add v plus u, we get the same result. So this is what we call commutative property. Commutative property under vector addition. It's a commutative property under vector addition. Commutative property. So u plus v is the same as, it's equals to v plus u. Very same thing. Very simple thing. So we also have got what called associative property under vector addition. So it says that u plus v plus w, if we start by adding u plus v first plus w, is the same thing as first start by adding v plus w then plus u. So that's what we talk about. U plus v, w, adding them first, plus u plus v, vector u plus vector v, adding them first, plus w is the same as u plus v plus w, adding them first, adding v plus w first. So this is what we call an associative property. It's a very simple property. So this same applies in real numbers. You know, real numbers is also an example of what? Of a vector space. So now that's a simple thing. It's an associative property. So we can also take an example inside a real number. So we can say, okay, or if we can also take an example of a vectors, it's the same thing. So let's start with commutative example of vectors, like proving those two laws by what called counter example. So if we let u to be what called 2, 3, and v to be what called 5, 6, and what called w equals to negative 1, 2. These are vectors in R2, belongs to R2. So u, we need to prove that u plus v first is the same as v plus u. So let's start with what called the left hand side. Left hand side is u plus v. So what is u? 2.3, 2 and 3 plus 5 and 6. This is the same as 2 plus 3, which is 5, and 3 plus 6, which is 9. So now let's talk about the right hand side. Right hand side. Right hand side. So this is just a right hand side. So the right hand side is v plus u. So v plus u will be what now? 5 and 6 plus 2 and 3, which is just 5 plus 2, which is what? Is 3 not 5? Is it 5? No, we're taking it as 5, sorry. So this will be 2 plus this will be 7. This will be what? 7. 2 plus 5 and 3 plus 6, 7, 9. So now this is what called 5.6, 5 and 6 plus 2 and 3 vector with two components 2 and 3. So we add the corresponding components together. This is 5 plus 2, which is 7, 6 plus 3, which is 9. So you see that this proves that no matter how you add, so they are still equal. So this part is equal to that part. So this is what we call a commutative property. So that means addition, the commutative property holds under vector addition. So this means that commutative property holds under what we call vector addition of VA. It holds. So we can also prove that other one. So if we insert a blank page, we can also prove that other one. So which is associative. Remember, we're having this U, V, and W. So a commutative property, what we are required to prove is that U plus V plus W is the same as I'm making a lot of mistakes, is the same as u plus v plus w. So now let's start by proving what you call the left hand side, so which is u plus v plus w. That means we're first adding what is inside the brackets, u plus v. So this is the same as equals to, what is vector this one? What is vector u? Is what? Is 2 and 3, 2 and 3 plus v is 5 and 6, then plus w, which is what? Negative 1 and 2. Negative 1 and 2. So we're starting by adding these ones first. So let me change the color here. We're starting by adding these one inside here. So if you add it, we will add the component wise corresponding components together. So this will be 2 plus 5, which is 7, which is 7, 2 plus 5, and 3 plus 6, which is 9. Then plus these, what you call, is still the same. These are minus 1 and 2. Minus 1 and 2. So now we add what we call 7 and 9, which is a result. Which is a result of these summation of these two vectors. 7 plus negative 1 is 6. That is 7 minus 1. And 9 plus 2 is now 11. So the sum of these three vectors, by starting adding u plus v first, is the vector with two components, 6 and 11. So now let's prove the right hand side. So which is u plus v plus w. This means we'll start adding what call v and w together and see if we find the same result. So what is u? U is 2.3 plus what is v? V is 5, 6. Then what is w? It's minus 1 and 2. So now this is just equals to, then this is 2 and 3 plus, we're adding these ones first. So now this one, 5 plus negative 1 will be what? Will be 4. It's just like 5 minus 1, comma 6 plus 2 is what? Is 8. So this is just equals to. So what is 2 plus 4 is 6, comma what is 3 plus 8 is 11. So you see, we find the same result. That means the associative property holds under what? Therefore, associative property holds under vector addition. It holds under vector addition. So that's what we are simply talking about. So now we also have got what to call the additive identity property. Additive identity property is adding 0 vector. Any vector plus 0 vector is that vector. So any vector plus 0 vector is that vector. We can take an example again. If we have that vector is 2 and 3, which we have that side, and we're adding 0, like this. So if we want to prove that u plus 0 is u, so it's a simple thing. You know that let's just prove what called the left hand side, which is just u plus 0 vector. So what is u? U can be 2 and 3. So if you can say the very same thing is 2 and what? Is 2 and 3, as in the example. Plus 0 vector is a vector with 0 components. if we're saying they're in R2, we suppose that U and 0 vector, they're in R2, they're in 2 dimension. That will be 0, 0. If in 3 dimension, 0, 0, 0, and dimension 0, 0, 0, comma, dot, 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 0. So now this will be what? 2 plus 0, which is 2, 3 plus 0, which is 3. This is the same as vector U, if you can see. Now it means that the additive identity property holds under a vector addition. Also, if we add a vector plus negative of that vector, we get a 0 vector. This is a 0 vector. So we get a 0 vector. So we are, remember, I said that, okay, for example, for quick example, you know that U, so you know that U is 2 and 3, that we are adding it with negative of 2, 3. In other words, we're multiplying it with the negative of that one. So we start with this, we'll start solving this thing. So this will be plus, we will distribute the negative. This will be negative 2, negative 3, negative 2, negative 3. So now this just equals to 2 plus negative 2, which is 0, 3 plus negative 3, which is 0. This is the same as 0 vector. So it means that this is supposed to be what? This is supposed to be what? A 0 vector. So now that's supposed to be a 0 vector. So also this we're also going to prove this one mathematically in Rn, not just these counter examples. Here I'm just giving you counter examples that this thing is true. So this property holds. So now we have got C times the scalar. So if we have got a vector inside V, a vector U inside a vector space V, and a scalar C belonging to a real number, so the scalar multiplication of C and U also belongs to a vector space V. That means this is a closure property under scalar multiplication. So we also have got what called the distributive property under what we call scalar multiplication. Under vector addition, this is the distributive property under VA. So this under vector addition, you can see. So this is C times this, C into this plus this. We're just distributing C, multiplying each vector inside the brackets by a what called a scalar C. Then this is scalar multiplication, adding together. So that's what we're talking about. C times U, vector U is CU, then plus C times vector V is CV. So also C plus D into U, this is just a distributive property under scalar multiplication, because firstly we're adding what we call scalars and multiplying by a vector. This tends to be a distributive property under scalar multiplication, but this one is under what we call a vector addition. So now this means that this is just C plus D, which is U. We distribute U again, the vector inside there, which is CU plus just like D times vector U. So this is just a distributive property under scalar multiplication. So we also have what called the associative property under scalar multiplication, which is C times DU. So C into times DU is the same as multiplying scalars first and then vector U. So that's what we're talking about. So now also the last axioms or the last property of this theorem is that a multiplicative identity property, which is 1 times any vector. So 1 times any vector, it is that vector. So likewise 1 times vector U is the same as vector U. So that's what we are talking about. So these are what we call 10 vector space axioms, or the properties of vector addition, abbreviated as VA, and scalar multiplication, abbreviated as SM. So you must master these axioms. They are very important when we go further. They are very important when we proceed with this course, when we also proceed to other topics and subtopics to other chapters, so they're also very important. So we must know these theorem. So they're a very simple thing to know. Now let's talk about proving them. We need to prove them in Rn. So we can prove them, all of them. So proof of the 10 vector space axioms. So now we'll be showing how to prove them. In this whole thing, we're using the same thing, that let U, V, W be inside Rn, be vectors, and CD belonging to these B scalars. We're using this assumption. So now, remember Rn is an n dimension where we have got what called n components. So components of the vectors. So the proof of 10 vector space axioms, proof number 1, we know that is a closure property under vector addition. What we are required to prove is that U plus V belongs to what called a vector space. Remember, V is vector space. Hence, the theorem is what we call 10 vector space axioms. So it really makes sense. So now, prove. We start with this left-hand side. You can see this is the left-hand side, which is what we call U plus V. So, if U is in V, we know that U has got what we call n components, which is U1, U2 up to Un, plus also V is inside, is the element, or it belongs to what called Rn. That means it must obvious consist of components V1, V2 up to Vn. When we add the two, we'll get what called U1 plus V1 component wise. You know, we add the corresponding components together. So this is U1 plus V1, this and this U2 plus V2 up to Un plus Vn. So now, since this guy and this guy and this guy also belongs to real number, what does that mean? These are real numbers. Remember, the components are real numbers. These all also belongs to real number. These all also belongs to real number. That means the vector itself also belongs to real number. And this thing, because we've got real numbers, this thing, whole thing, is also inside Rn. So this is inside Rn. Everything is inside Rn. So if it's inside Rn, we can conclude that this is therefore inside V, because Rn is the same as is the vector space that we're dealing with. We're in Rn. So that's simple thing. We're in Rn. The space that we're in is in Rn, which has got some vectors. So the method that I use to understand this, when they talk about vector space, if I'm not using, I'm just using straightforward definition and what called simple understanding. Because we talk about vector space, I just well defined it as vectors in space. The space is Rn, is n dimension, and inside that Rn there are vectors, and those vectors, they can add each other. We can also multiply them with a scalar. So that's a simple understanding. That's how I understand what call this vector space. So now this is simple because we're adding two vectors U and V inside Rn, which is this. But we know that U1, U2, whatsoever, they are components and they are real numbers. So now this is the same as U1 plus V1. Since this belongs to a real number, that means the whole vector is also inside the real number. This thing is a real number. And this thing is also inside Rn because there are three components. It's like XYZ plane. So therefore it means that this thing is inside what? A vector space. It's inside Rn, which is a vector space. Remember, the vector space that we're talking about is Rn. So this thing is just inside Rn again. That means it's inside what called vector space V. So this is what called a closure property under VA holds. This means that the closure under property under VA holds. That's simple proof. So now let's go to number 2. So now we've got proof number 2. So what we're required to prove is a commutative property. So what we're required to prove is that U plus V is the same as V plus U. Remember, was U and V, W, they are inside Rn. So let's prove the left hand side of the equation, which is just U plus V. So you remember U is this U1, U2 up to Un, and V is this V1, V2 up to Vn. So is this thing. Now we add what called the corresponding components. So that's U1. When we're adding two vectors, we're adding corresponding components. So this is just U1 plus V1, which is U1 plus V1, U2 plus V2, U2 plus V2, up to Un plus Vn. So now it's the same thing, that since this guy, U1, U2, up to Un, V1, V2 up to Vn, they are element of real numbers. So now it means that also if you add them, they also belong to real number, because addition under real numbers is commutative. It's closure. The closure property under real under R is holds or is satisfied. So now U1 plus V1, since U1 plus V1, U2 plus V2 up to Un plus Vn belongs to R or to real number, this means that we can now have what call, we can now start with V1 plus U1, V2 plus U2, because these individual elements, they're inside R. Therefore, Vn plus Un. We can separate again. This is the same as V1, V2 up to Vn plus U1, U2 up to Un. And what is this guy? It's a vector U. What is this guy? It's a vector. This one is a vector V. This one is a vector U. So this is the same as V plus U. And this is equal to the right hand side. That's how simple we are proving this thing. It's a simple thing. Therefore this means that the commutative property holds. So now let's go to the proof number 3, which is an associative property. This is a little bit complicated, but very easy steps to follow, very easy procedure to follow. So now we start with the right hand side with what we are required to prove is that U plus V, we are adding them first, plus W, it's equals to U plus V plus W. So now let's start with proving the left hand side until we get the right hand side, if possible. So now U plus V, adding them together, plus W. But what is U? U is this guy. We do the square brackets because we have round brackets also inside. So this is U1, U2 up to Un plus this guy, which is V1, V2 up to Vn, plus W. W is also this one, which is W1, W2 up to Wn. So now we add these two first. This will be U1 plus V1, which is U1 plus V1, U2 plus V2 up to Un plus Vn first. So, and this one we're just rewriting it in the next step. So now we need to add this with that. So this will be U1 plus V1 plus W1. We're just adding this with this element wise, you know this thing. So this is simple as this plus this, which is this, and simple as this. No, I want to change color. Simple as this plus this, which is this, and simple as this plus this, which is now this. So that's what we're doing. So that's adding them. You know that we add what we call the corresponding component as always. So now, since these, the blue one, since this addition of this and this belongs to a real number, we know that u1, u2 up to un, v1, v2 up to vn, w1, w2 up to wn, they belongs to real number. So even their addition also belongs to what? To real number. So now we can commutate inside anyhow. So that's why we can have what called now the vector also belongs to R. That's what we're saying. So now we can group the two because they are what call, they are now real elements. We can group them however. So that's why we have got u1 and we group these two guys. U2 plus, we group these two guys together. We're just grouping these together. Grouping these together. So that's what we're doing. So up to un and group these guys together, v1 plus wn. So then when you take these, this is the same as u1, u2 up to un plus, because we're adding these ones together, which is v1 plus w1, v2 plus w2 up to vn plus wn. But what is this guy? This guy is the same as v plus w, because these are components of vector v and vector w. So now then that means this is u plus v plus w. Thus this equals to the right hand side. Therefore the associative property holds under what? Vector addition. That's how simple we are doing this thing. So now let's go to the next proof, which is what we call additive identity property. This one is very simple. That is proof number 4. So we are required to prove that u plus 0 vector is that vector u. So that's how simple we are talking about this. So now we have these guys. We need to prove what called the left hand side first until we somehow get the right hand side if it's possible. So now this is the same as the left hand side is just vector u plus 0 vector. So this thing is, what is u? U is this. Remember, u is in Rn and also 0 vector is also in Rn. So this is just u1, u2 up to un. Plus, what is this guy? So this is just a 0 vector. So this is also 0, 0 up to what we call 0. So it's 0, 0, 0 up to 0. So that is that is a 0 vectors in nth dimension. So now we now add what called the corresponding components, which is just u1 plus 0, u2 plus 0 up to un plus 0. So then u1 plus 0, this is just u1, u2 plus 0 is just u2, up to un plus 0 is just un. But this guy, if we recall, it is just what called u. And this is equals to what called the right hand side. So that means the additive property holds under vector addition. It's a simple stuff. So now it's a simple stuff, as you can see. Now we can go to the proof number 5. So we have this proof now. So what are we required to prove? We are required to prove that u plus the negation of u, it's a 0 vector. It's an obvious case, but we don't do that. We just have to prove, to show this stuff. So now we need to prove what called the left hand side. So proving the left hand side, which is equals to u plus negative u, that's a vector, remember. So now what is u? Is this guy, it's u1, u2 up to un, plus, now what is also u is this one, but we are multiplying by negative. Just take as negative, or just take as this scalar is just a negative one. So now this is just what called, when you multiply, we remove the brackets, this thing will become negative u1, negative u2, up to negative un. So that's what we're talking about. So now we add this and this. That means this plus this is like this minus, is like u1 minus u1. For adding this and this, u1 plus negative u1 is like u1 minus u1, u2 minus u2, up to un minus un. This is 0, 0, up to 0. And 0, 0, 0 is just a 0 component. It's just a 0 vector, sorry. It's just a 0 vector. So this means this is a right-hand side. That means when we add a vector with its negation, we get what we call 0 vector. So therefore this means that the additive inverse property holds. This is called what called the additive inverse property. Additive inverse property. So now we also have proof number 6, which is what called the closure property under scalar multiplication. So now it's a simple proof. We just have to understand some simple steps. So we are required to prove that C times vector u belongs to a vector space V. So to prove this, we need to consider C times u, which is scalar multiplication of C and a vector u. You know what is u? A vector u has got what called n components, which is C times u1, u2 up to un. This is just equals to, we multiply each component by a scalar C. This results into these C times u1, cu1, C times u2, cu2 up to C times n, cun. So then since these guys, C belongs to real number, and also u1, u2 up to un also belongs to real number. So this means that cu1, cu2 up to c also belongs to real number. Then this whole vector, this whole thing also belongs to real number. This whole thing also belongs to real number. So what does that mean? It means that C times vector u also belongs to what called to the vector space V. Then the closure property under scalar multiplication holds. So it's a simple proof, just to understand a few procedures. So now we've got what called proof number 7, which is just what called the distributive property under what called vector addition or VA. So now we are required to prove that C times u plus V is equals to C times u plus C times V. We multiply each vector inside brackets by a scalar C. So then let's start by proving the left hand side. So this is C times u plus C into u plus V. So but we know what is u. U is this one, it's u1, u2 up to un, plus we know also what is V, it's v1, v2 up to vn. So then we first add what is inside the brackets and then multiply by a scalar. So now this is u1 plus v1. When you add this one and this one, it's u1 plus v1. When you add this one, it's u2 plus v2 up to, when you add this one and this one, it's un plus vn. So now we then multiply each component here by what we call a scalar C. That's what we're doing. This is C times this, which is just u1, C times u1 plus v1. That's why we have a bracket C into brackets, because there are two components inside adding each other. This is just C into u1 plus v1. Then C times that one again, which is C, just what to call C into u2 plus v2 dot comma C also into just like un plus vm. So now then we remove the brackets. So therefore we remove the brackets. This is just C1 times U1. You know that's also the scalar what? That's also the distribution. But we are now doing that distribution adding two components. That means we just multiply that each component by a scalar, which is just C times U1, which is CU1 plus C times V1 CUV, likewise up to C times UN, which is just CUN plus C times Vn, which is plus C times Vn. So now we collect those same components, which is CU1, C. We collect these together. So this is CU1, CU2. This means that because we're adding, this just means that we're adding this plus this vector. When we take out C, we now have C is a common factor. We now have U1, U2, UN. You know that if we need to multiply, we just multiply each component. So we're allowed to take it outside as a common factor. So plus also, we also take this one out as a common factor. So then we've got what called the remaining thing is vector V1, V2 up to Vn. But we know that this is the vector U and this is the what vector V. That is just the same as C times vector U plus C times vector V, which is equals to the right hand side. Therefore, this means that the distributive property holds. So that's simple proof, which is proof number 7. So now let's talk about proof number 8. Now here we're proving the distributive property under scalar multiplication. So the distributive property under scalar multiplication holds. So we have what we are required to prove here, which is just C plus D. We add them first times vector U, so which is equals to this. We need to start with proving what called the left hand side. So left hand side, which is C plus D, then times this U. Then we know we're just substituting in terms of vector U. We put what called those vector with those nth components inside U1, U2 up to UN. So then we this is a scalar. We multiply these to each component inside. This is just this multiplied by this component, this scalar multiplied by this component, this scalar multiplied by that component. So now then we have again, we distribute inside. We distribute this what we distribute these component to each scalar, that is C times U1, which is CU1, plus D times U1, which is DU1, likewise up to C times UN, which is C times UN, D times UN, which is just like D times UN. So now when we have something like this, we collect the same thing, these and these together, which is CU1, CU2 up to CUN, plus these together, which is DU1, DU2 up to DUN together. So then thereafter we take out here, we can see that there's a common factor of C. C is multiplying every component inside there. So now we take out that C, then we have what called C into U1, U2 up to UN, plus also we take out D, which is just remaining with D into U1, U2 up to UN. But we know what is this vector. So this vector is a vector U. We also know what is this vector. This vector is a vector U, and that other vector is also vector U, but we're just taking out the common factors. So now this means this is the just right hand side. We just proved what is required. So this means that the distributive property holds, or the distributive property under scalar multiplication holds. While finishing these 10 vectors, proving these 10 vector space axioms, it's very much important to know this. This does not happen under Rn only. It can also happen under polynomials. It can also happen under matrices. So we will also dwell on this, but this time around we won't go through each and every proof like this that we're doing, because it's so much tedious and laborious, as you can see, but very simple. So now we have what we call proof number 9. So what we're required to prove is that this is what we call associative property under scalar multiplication. So now this is C times C into D times vector U is the same as multiplying scalars first, which is C times D times vector U. So now let's prove these left hand side, which is just C into du. Then we just need to substitute where there's u, vector u. You know that u is equals to u1, u2 up to un, because this is inside Rn, that's the space, the dimension, nth dimension. This is what we call n dimension. So now we have C, this is the same as C into D u1. Here in place of this vector u, we put this guy. So this is u1, u2 up to un. So this is the same as C. Then we multiply inside first by this scalar to each component. This is D times u1, which is du1. This times this one, which is du2. This times this one, which is up to dun. Then we then multiply by C. This will just be, let me show you something before. Okay, let me show you something before I talk about this step. So this is just multiplying. This will be CD u1, CD u2 up to CD un. So now we can group the scalars together like this. That's why we have this step, CD grouping together u1, CD u2, CD un. This is a common factor. We can take it out. We can take this nonsense outside. So now this will be CD here. Then we have what we call inside, sorry, u1, u2 up to un. But what is this guy? This is just a vector what? A vector u. So this is just equals to CD times what we call a vector u. So this is just what we call equals to the right hand side. Does we prove this thing? Therefore, this means that associative property or under scalar multiplication holds also here. So the last proof, which is the last thing, which is a multiplicative identity property, that is also under scalar multiplication. So now we are required to prove that 1 times any vector is that vector. 1 times vector u is equals to vector u. So let's prove these left hand side until we get the right hand side, if possible. So now we have 1. What is vector u? 1 times what is vector u? It's u1, u2 up to un. So this is the same as, this is a scalar. 1 is a scalar. Then we multiply a scalar. We multiply each component of a vector by a scalar. So that's why we have 1 times u1, 1 times u2 up to 1 times un. So now 1 times u1, so it's just these two components which are real numbers multiplying each other. Then we get u1, we get u2 up to un. But this is the same as what? As a vector u. Therefore, this is the right hand side. Therefore, the multiplicative identity property holds. Okay, the multiplicative identity property holds. So in the next video, which will be part 2 of these vector spaces, we'll be considering this example. That's just that in case we just have to shorten the videos so that it won't be 4 hours or 2 hours. It won't be that long. So 1 hour 20 minutes is enough. So we'll just have to upload another video, then doing the examples. Now you see down the example is no longer what call R, is now what called polynomials. This is a very interesting example. So that we're going to get, that we're going to to work on in the next video. So if you find this thing very interesting and opening your mind in terms of the linear algebra course, so you can support me by just simply liking, sharing and subscribing to my channel. So I hope you have a wonderful time with me here, and I believe that you were following what I was doing, and I'm really looking forward to upload more videos and to do more things to make these mathematical concepts very simple to you and very understandable. So if you have any question, any query regarding this or linear algebra course, you can pose, or you can write the questions in the comment section. Then I will those questions will be considered and responded accordingly and in due time. So thank you very much for being with me. I love you so much. Enjoy the video. Thank you.